We'll wait for 2 minutes, ma'am. Many are joining now, ma'am. Please. Ma'am, you please switch on your video for a few minutes, ma'am. I will just take photograph. Thank you, ma'am. Sir, I think we can start. Yes. A very good morning to everyone. On behalf of Department of ECE SRM Valliammai Engineering College, I take this opportunity in welcoming you all for this AICTE ISTE sponsored induction bar reflection program on the title FPGA for Low Power IoT. So we have done with our inaugural session, and the second session is being handled by Dr. Yes. Dr. K. Sivasundari ma'am. I take this opportunity to introduce Dr. Sivasundari ma'am to the participants. Ma'am, the screen is visible.
Yes.
Yes. So Dr. K. Sivasundari completed her BE in Electronics and Communication Instrumentation Engineering from Annamalai University and ME in VLSI Design from Kalasalingam Engineering College and PhD in MEMS and Microelectronics from Annamalai University. Currently, ma'am is working as Post-Doctoral Fellowship in Center for NEMS and Nanophotonics, Department of Electrical Engineering, Indian Institute of Technology, Madras. Welcome you, ma'am. So her expertise includes experience in MEMS and microelectronics fabrication process, characterization tools such as vacuum probe station, parameter analyzer, optical profiler and ellipsometer, and design of mask and generation of GDS2 files. And she has also has more than 10 international journals and for her credit, and she has filed a patent and a register for MEMS pressure sensor using PWM technique. Thank you, ma'am, for accepting our invitation. And for today's session, ma'am will be delivering on the concept of FPGA for MEMS application. Over to you, ma'am.
Thank you, Ms. Dr. Usha Bhanu, ma'am, and thank you for welcoming me for this seminar. And I'm just uploading my PPT. Ma'am, is my voice audible and is my slides are visible?
Yes, ma'am. Yes, ma'am. You can continue, ma'am.
Yeah. Good morning to the participants. As I think ma'am has introduced me well, and today I'm going to deliver on the topic FPGA for MEMS applications. Uh, okay, today I'm especially going to concentrate on the sensors that are available in for IoT applications and how those sensors can be integrated with FPGA particular FPGA so that the low power consumption and flexibility of design can be obtained. So this is the one line of the today's topic. So to start from it, let us see what is the necessity for sensor in an IoT applications. IoT in a very layman thing is to say that Internet of Things is all about automation of a location from a remote region. So if in such type of cases, we will, what are the things we need to collect data at different points in the location where we are in the location which we are accessing from a remote place. So how we can collect those data? For example, if you are, let us consider a very simple application that I am going to control my house from a remote location. So the things we will be monitoring is the condition of my house. So the simple thing is who is in the house, what are the at each locations of the house, what are the things, what are the happenings, like whether the switches light is on. For example, if I am having an RO pan, if the RO is switched on, and if I have to switch on a particular heater at a particular time, how to do that. So so we have to collect the data points. So that we will know the current live situation of our house, of the house when we are remoting it from when we are accessing it remotely. So how we will be collecting these data points. So that is where the sensors play a major role in IoT, in Internet of Things. So what I have currently said is a very simple application, but when you go for complex applications like monitoring a radar system from a remote location, or monitoring a patient conditions from a remote location, or controlling a plant from a remote location. So there we need n number of data points to be collected to precisely control each of the situation. So without sensors, IoT would not be possible, to be literally frank. But so millions of devices are connected with sensors like wearable smartphones, etc. And indeed, sensors play an essential role in Internet of Things. As I said before, the sensors are used to gather the information from the surroundings so that we can efficiently control the remote location. So the types of sensor which commonly used in a IoT application is definitely a temperature sensor, which will be used to monitor a boiler temperature, or it can be a patient body temperature, or anything. So so this, even if we say as a temperature sensor, it's not a simple sensor which measure some 0 to 100 degree. We may need to sensors to measure 0 to 1000 degrees according to the situation place we are going to use the temperature sensor. And next one is the proximity sensor. Proximity sensor is the sensor which is used to detect the movement of a particular object or a particular person, so such that we can efficiently control the application, which you can control the application. For example, if you're going to because some shops will have automatic opening and closing door closing system. So there they'll be using the proximity sensor. And similarly, the automatic water tap, that where we can just insert it and water will be coming when it detects some motion. So these proximity sensors is one of the primarily used sensors while monitoring a live location. And image sensor is used in different places, like radar. Capture the images of radar will be these image sensors will take the images from in the radar location, or the thermal image of a thermal plant. So next one is the accelerometer. So this accelerometer sensors are the sensors which are used to detect the vibrations in a particular particular location or particular object. So IR sensor, again, it's used for temperature measurement, or it can be used for some some movements. So n number of application sensors can be built with this IR. Next one is a pressure sensor for monitoring a human blood pressure, or it can be a boiler pressure, or it can be a simple air pressure from a airbag. So humidity sensor is used to detect the room humidity. And again, motion sensor. The proximity sensor and motion sensor is the motion sensors will capture the linear movement of the any object, but proximity sensor will detect the exact location of an object. Next one is a smoke sensor. Smoke sensor or gas sensor, where we can use to detect gas from an unwanted particular gas from an unwanted gas from unwanted unrequired places. So in that such cases we need gas sensors or a smoke sensors. Next, I think most of the people, I don't need to say much about field FPGA. So FPGA is a field programmable gate array. So what is the significance, or what is the use of this FPGA? So there are so much programmable devices, but most of the programmable devices are once programmed, or it can be only once programmed, or it can be already programmed. So there is such and some programmable devices can be configured in a particular manner, so it is not user friendly. But FPGA is the only programmable device where we can on field, where we are using on field, we can use the FPGA can be used on field to program it, and we can test it on field. So that is where FPGA got more significance comparable to other programmable devices. So FPGA is generally will consist of small programmable blocks as shown here, and they will have interconnect resources. So we can individually program the we will calling as CLB, configurable logic blocks. These CLBs can be individually programmed, or it can be four CLBs can be connected together, and it can be emulated with one particular program. It depends on the architecture of particular FPGA, or it depends on the requirement of an application. Okay, so what is the major difference between ASIC and FPGA? What is the thing is, in a same FPGA we can implement different ASIC, but we cannot so in ASIC is dedicated for a single application, but all the applications that are done in the ASIC can be done in FPGA. So that is the main difference between the ASIC and FPGA. Both has its own advantages and its disadvantages. So in this way, this programmable field programmable gate arrays are gaining more interest than the commercially available ASIC systems. Next, MEMS. Why it is MEMS, and why it is not a macro sensor is the two. So that is what we are going to cover in this topic. One is so MEMS is a micro electromechanical systems. So with this MEMS, we'll be able to integrate it directly with the signal conditioning circuit. So that is the advantages of going for a MEMS sensor rather than going for a conventionally available sensors. So what is MEMS? So a MEMS device is a miniaturized device or a structure. So it can be MEMS can be a simple transistor or a simple resistor or it can be a structure. For example, a pillar, or it can be a channel, fluidic channel. But so it can be either a device, miniature device, or a microstructure. And in MEMS we'll be definitely having at least one mechanical structure. This mechanical structure can be a fixed pillar, or it can be a complex moving structure. And any critical dimension of a MEMS device will be below micro level to lower scale of dimensional spectrum. So these MEMS sensors are fabricated using the microfabrication technology. So they will go hand in hand, but MEMS is also having its exclusive particular exclusive fabrication steps that should be used for MEMS devices. So MEMS system in general consists of a micro sensor, micro actuator, microelectronic, and microstructure. But here in this topic, we are concerned only about this micro sensor, and even micro actuator play a vital role, but I'm not going to concentrate much on micro actuators. I'm just going to concentrate on micro sensors. Microsensor, common examples of microsensors are pressure sensor, accelerometer, temperature sensor, and biosensors. Biosensors may include pH meters, glucometer, microorganism sensor, and so on. So what I'm put here is the simplest available MEMS sensor that can be integrated for IoT applications. So this pressure sensor. So MEMS pressure sensor works on 4 different mechanisms. One is a piezoresistive pressure sensor, capacitive pressure sensor, resonance pressure sensor, and piezoelectric pressure sensor. In piezoresistive pressure sensor, any pressure will be converted into change in resistance. So what we can do is we can have a diaphragm that will consist of this piezoelectric material. So when we apply a pressure, the diaphragm will deflect and cause the change in the resistivity, and it will correspondingly will change the resistance of this resistance. The change in resistance will be directly proportional to the pressure sensor. So when we take a capacitive pressure sensor, the change in pressure will be detected in terms of change in capacitance. So in general, we'll be having 2 parallel plates. So one will be fixed and the other will be movable. The fixed plate, so the movable plate will deflect according to the change in the pressure. So that is change in distance will cause the change in capacitance in such type of pressure sensor. The next one is the resonant pressure sensor. So we'll be having a hanging structure. For example, assume a cantilever beam kind of cantilever beam. So this cantilever beam will have a particular natural frequency. But once a pressure is applied, the natural frequency will shift to natural frequency plus the frequency due to the pressure, change in frequency caused due to the pressure. So there will be a change in the shift in the natural frequency of the cantilever beam. So the amount of shift will be measured as the change in pressure. Next one is a piezoelectric pressure. So here the piezoelectric pressure will be so here the piezoelectric materials will be used along with the pressure sensor. Whenever there is a change in the pressure, the charge across the piezoresistive material will change due to the deformation of the material. The change in the amount of change in charge will be measured as the change in pressure. Next is the accelerometer. So as I said before, this accelerometer is used for detecting the vibration in a system. Here also there are 3 types of sensing mechanism. One is capacitive, and other one is the capacitive pressure accelerometer, resistive accelerometer, And the last one is the piezoelectric sensing. Here, here the green ones are the fixed plates, and the orange one is the mobile plate. So this mobile plate will move either in the horizontal direction if the vibration is in the longitudinal vibration occurs, and orange color this orange color mass will move up and down if there is a transverse vibration. So when there is a horizontal vibration, the distance between the orange arm and the green arm will change. The corresponding change in so there will be a change in the capacitance. So the corresponding change in capacitance will be correlated with the occurred vibration. And next one is during the transverse vibration, the proof mass or this proof mass will move upward. So at that time, the total overlapping area between the orange finger and the green finger will vary. So in this case, the change in capacitance is caused due to the change in the overlapping area. This change in capacitance is directly proportional to the transverse vibration. Similarly, so all these accelerometers are based on the proof mass. Here also we can see we have four arms, and we have four piezoresistance connected to it. So whenever there is a vibration, this piezoresistor will be subjected to deformation that will cause a stress in the piezoresistive material. This stress or strain will cause the resistivity of the material to change. If there is a change in resistivity, the resistance of the material will also change, because R is equal to rho L by A. So this change in the piezo resistance will be directly proportional to the amount of vibration in the system. So here we won't be able to detect the longitudinal vibration, and it will be mostly used to detect the transfer vibration. Here in the piezoelectric sensing, we will have a cantilever beam, and we will be placing a piezoelectric material. This piezoelectric material will be subjected to pressure. When vibration occurs, there will be a large movement of this cantilever due to this proof mass. So that is the use of a proof mass. To amplify the deflection, we will be using proof mass in most of the accelerometers. So this will vibrate as it vibrates. There will be a strain will be crossed across the piezoelectric material. This strain will cause the change in the will be directly change in the charge across the piezoelectric material. This charge will be converted into voltage by using the top and the bottom electrode. So in this case, that we will be directly getting a voltage output from this sensor. See, though here we are getting change in capacitance, change in resistance, here we will be directly getting a change in voltage. So in such type of cases, it will be very easy to do the signal conditioning, in particularly for IoT application. Here also we will be able to do the same, but we need some small signal conditioning circuit to convert the capacitance to corresponding voltage, and or a signal conditioning circuit to convert the resistance into corresponding change in voltage. So these are called DC accelerometers, since the output will be converted to a DC voltage. Here mostly here an alternating voltage will be produced across the piezoelectric material due to the vibration. So it is called an AC accelerometer. So the most common application where the NEMS accelerometers are used is seismic meters, airbags in automobiles, and structural health monitoring. Structural health monitoring is an application where we can find the health of a structure. As the structure gets old, will be the vibration of the building. Am I not audible?
Ma'am, you are audible, ma'am.
Okay. So structural monitoring, health monitoring is one of the applications where we can use what happens is the building will the frequency of the building vibration in a building will increase as the number of years increase. So according to the change in the vibration, we can estimate the lifetime of the building. That is one of the areas where we can use this accelerometer explicitly, and we can control the or monitor the health of an structure. So these are most commonly used in most of the bridges, particularly in Delhi, to monitor the remote monitoring of the lifetime of the bridges. And next one is the temperature sensors. Temperature sensor are basically based on, again there are three type of temperature sensors. One is based on thermistor, where next one is the piezoresistor, and next one is the bimetallic films. So bimetallic films. In the in the thermistor, whenever again it's a resistive material. So this resistive material temperature will resistance will change according to the change in the temperature. And the next one, again, piezo resistors also can be used as the temperature sensor, because the resistivity not only depends on the strain caused on it, but also on the temperature. Whenever there is an increase in temperature, there will be a increase or decrease in resistivity of the piezo resistive material. So depending on its thermal temperature coefficient of resistance, either the resistance will decrease or increase due to the change in, increase in the temperature. In that way, change in resistance is measured in terms of change in temperature is measured in terms of change in resistance using the piezo resistive method. The last one is the bimetallic films. So bimetallic films is the one. So here so the beam will be made up of two different materials. So the bottom will have high expansion coefficient, and the top one will have low expansion coefficient. So what is the use? So what is this expansion coefficient is? For per degree increase in temperature, each material will expand to some extent. That was defined by the parameter called expansion coefficient. So we'll be taking two metals which is having two different expansion coefficient. So what happens is, when the temperature increases, one of the material will expand faster than the other material. So what happens is, this will cause the bending of this. So this is fixed at one end and it is free at the other end. So what happens is, the deflection will happens in the direction of the direction where the on the direction of the material which has the high expansion coefficient. In this case, we have this red material is having high expansion coefficient. So the once the temperature increases, this material will expand for fastly. What happens is, it will cause the top material also bend according to the temperature. So this total deflection caused due to thermal expansion will be proportional to the increase in the temperature. This is one of the MEMS technique which is ideally used for in many of the MEMS based temperature measurement. So both all the three are MEMS based measurement technique. The most commonly used are this bimetallic films and piezo resistors. So the application is abnormal increase in temperature in home, building or factory can be identified, and it is a non-contact measurement. So we don't need to put anything on it to measure the temperature. That is why they are used in IoT applications. And the last one and the interesting one is the biosensors. So biosensor. So here the transducer mechanisms are electrochemical, optical, thermometric, and magnetic. So electrochemical method is based on particular material will have electrical conductivity. Particular material doesn't have electrical conductivity. Depending on that, we can detect the enzyme detection, or we can detect um, any viral detection. Anything can be done using this electrochemical method. And next one is the optical method. So certain materials, certain chemicals have different chemicals will have different reflectivity based on the enzymes, or it can be any RBC or WBC. Depending on that, the optical reflection will change. So based on that, we will be able to detect the type of biocursors we want to detect. Biocursors we want to detect. Sorry, biomarkers we want to detect. Next one is the thermometric method. It is depending on the amount of heat required to attract some amount, change the particular amount of one type of enzyme to another type of material. That can be that can be done using thermometric method. So we will have a known material, and if you apply certain amount of heat, it will be converted to corresponding different material. If this known material is contaminated with some biocursors, some external element, the total amount of chemicals changed from A to B will reduce. That amount of change will be directly proportional to the amount of biomarkers present in a fluid. Last one is the magnetic method. It is very simple. We have each material will have different polarities. Depending on the polarities, we can bifurcate the materials. That is called magnetic transducer mechanism. So, sorry. So how they are used? They are used for glucose level measurement. These glucose level measurements are done using electrochemical methods. So whatever you're seeing in your glucometers, the chip we insert it and put the blood on it is based on this electrochemical method. Once we put a drop of blood on the particular strip, what happens is it will increase the amount of conductivity through that chip. So in that, if the glucose is present, if it is a normal blood, the conductivity will remains the same. In that way only they are detecting the glucose level using glucometer. So these glucometers are based on electrochemical method. And next one is the enzyme detection. So enzyme detection is the one I have shown here. Here you can see a piezoelectric surface, and we have a channel, fluidic channel. They have two input electrodes. What are electrodes? These electrodes will convert the charge generated by the piezoelectric substrate to a corresponding voltage. So this substrate along with these two electrodes will be coated with an so this is called antibody. So and we'll be passing the analyte, that is the fluid which contains the target antigen. So what happen is, so if for example, there is a antibody called A, and it attracts the antigen B. And if this fluid which are passed through the channel contains the particle B, that will be attracted towards this antibody, and it will settle on it. So what happens is the total mass on the piezoelectric material will increase. The change in mass will be deducted as changing in the voltage flow through this channel. So in this way, we will be able to deduct the amount of analyte that is present in the sample. This is one of the methods for detecting any enzymes or antibodies. So this is a very versatile method which is used for enzyme and antibody detection, and this will also be coming as a thin strip. We don't be able to see it particularly, but once we put a drop of it can be anything. It can be an urinal extract, or it can be a blood. So anything, it depends on what is the type of measurement we are going to do. But this is one of the efficient method. Now they are significantly started developing. And so these are some of the commonly available MEMS sensor that can be used for. So these biosensors can be used for automation of your health monitoring in system in hospitals, or automation of health monitoring in a research lab for the development of drugs and vaccines, or particularly drugs. And next to whatever we saw, these temperature sensor, accelerometers, and pressure sensors can be used for varied amount of applications, from automation. Most of these sensors will be used for IoT application based on automations, automobile industries, because as the e-vehicles are coming forward, there is a wide scope of using MEMS sensors for automation, and this can be remotely controlled. That is the target of the automobile industry. So most of the research we are going on of using these sensor for automobile in such a way that it can be integrated for IoT applications also. Okay, next we'll come to the topic. So what is the use of this how we are going to integrate this MEMS? First question is why we are going to integrate with FPGA? Why not we have a signal conditioning circuit rather than an FPGA? Here there are two types of, before going to that, there are two types of MEMS and electronic integration. One is called hybrid integration, and other is called monolithic integration. In hybrid integration, we'll be having a separate. So this is an example of hybrid integration. So we'll be having a sensors as a separate chip, and we'll be having an CMOS IC that is there's another chip which has the signal conditioning circuit for this MEMS chip. For example, as I said, we'll be having change in capacitance, change in resistance. Those change in resistance has to be converted into, or change in voltage. That will be, so change in capacitance will be caused by this MEMS chip, and change in capacitance will be converted into voltage, and it will be further processed depending on the application. For example, if we have to transmit wirelessly, this will be converted to voltage, and that will be amplified, and it will be transmitted to remote location using a transmitter. And in that case, we need to process the signal in such a way that it can be transmitted for a particular distance of interest. So this is the first one, hybrid integration. Next one is the monolithic integration, where in the same chip will have the MEMS device, and its corresponding signal conditioning circuit will also be present adjacent in the same substrate. That is, same silicon substrate will have the device as well as its signal conditioning circuit. So what is the advantage and disadvantage of these both? Is the first case, we can if we have a new method of signal conditioning, what we can do is we can remove this IC and we can insert some other IC which have better signal conditioning circuit for this corresponding MEMS sensor. So in that way, it can be versatile to design and program, and the integration is easy here because we don't need for while fabricating the MEMS sensor, we can concentrate on the performance of the sensor alone. We don't need to worry about how it will be integrated, how efficiently we are going to integrate it with the signal conditioning circuit. So once the MEMS devices performance are satisfied, we can have design a separate IC that is having a signal conditioning circuit that is suitable. We can have a signal conditioning circuit chip that so that signal conditioning circuit can be efficiently designed according to the MEMS sensor that has been fabricated. So in that way, we have an advantage of having a good MEMS sensor as well as a good signal conditioning circuit for the MEMS sensor. So both will. The only thing is the integration. So integration that is where the disadvantage is. So the integration is we have a multi-layer. We should have multi-layer package substrate, and it will be connected through an independent bonding method. And what will happen is sometimes if the some most of the time this bonding may be getting damaged earlier, so its lifetime will be little bit less, and integration is also a very lengthy process. So next is in the monolithic integration, the thing is there is a the process flow adapted for the fabrication will be complex and lengthy, and it will take a long time to do the optimization, and there will be a bottleneck. So we are doing the integration, we are taking the same substrate, and we'll be putting the sensors and as well as the electronic elements on the same substrate. So some of the MEMS process will not be compatible with the electronic components, and some of the electronic components will fabrication will hinder the MEMS IC also. So we need to compromise in slightly in the sensor fabrication as well as in the signal conditioning circuit. So in such cases, there will be a limitation in the design of the system. But the thing is, the reliability will be more. Once it is designed and it is working perfectly, the lifetime and reliability will be more in the monolithic integration. But the process flow will be very lengthy, and the time for manufacturing such type of monolithic integrated ICs will be a very long process, and it will become more costly. The cost effectiveness will not be there. That is the disadvantage. So we can go for either of this, but it depends on depending on the application and specific what are the application and spec of the design. For example, I don't need to have the compromise between a single conditioning circuit as well as the MEMS IC. Then you go for hybrid integration. When you go for I need more reliability and more long term, go for monolithic integration. So it depends on the requirement and the requirement of the application. Now I'm going to present 4 case studies. Okay. Before that, so here is the role of FPGA comes. So instead of having a CMOS, so in here we can replace this integration, hybrid integration with the FPGA IC. Or what we can do is we can just have a simple signal conditioning circuit for connecting the MEMS chip to the FPGA. So in that way, we don't need to spend much time on designing this signal conditioning circuit. We just need to have a we just need to transport the electric parameter in the sensor to the FPGA, and all the other processing will be taken care in the FPGA, and it can be resent to the IC also if required, like a feedback loop. And what is the use of doing so? So what I cannot I the same sensor can be used for different type of application. So if there is let us assume there is a MEMS manufacturing company. If they were able to have different targeted group of peoples who will be using this IC, that is the different markets, the same sensor can be used for automation, same sensors can be used for aerospace application, same sensors can be used for automation industry also, automobile, aerospace and automation. So so there will be a wide market for the MEMS engineers, and at the same time the consumers who are using those sensors, so they can just buy that MEMS IC alone, and whatever the signal conditioning circuit they need to have, they can do on the FPGA system, and they can use it for their application. So that is where the integration of MEMS and FPGA comes into picture in the hybrid integration. So in the next few slides, we'll be seeing some case studies. Case studies where the integration of MEMS IC has been done with the FPGA application with FPGA. These are mere case studies I have taken from few papers after some literature survey, and I have given the reference of those paper also in the bottom of the slide. If you want, you can note it from there. We are taking three case studies. One is MEMS acoustic array embedded in a FPGA based data acquisition. Next one is the Spartan 6 FPGA based MEMS accelerometer processing electronics for navigation. The last one is the control of MEMS disk resonant gyroscope using FPGA platform. Here in most of the devices, most of the cases, they have a MEMS sensor with a simple signal conditioning circuit for converting the signal from the sensor and to a corresponding voltage or current or whatever electrical signal that can be processed in an FPGA system. This is how all on that basis. So the rule is same. We will have a MEMS sensor. We will have a simple circuit that will convert the parameter measured in the sensor to corresponding voltage signal, and the voltage signal, further processing and further analysis of those signal will be made in an FPGA system. The first one is the MEMS. First one is the MEMS acoustic array embedded in a FPGA based data system. So here they have a MEMS acoustic array. So here acoustics is the method where we can remove the noise produced in the sound and across the room, and makes the sound clearer to a larger extent of people. That is the acoustics. So MEMS acoustic array was made up of MEMS microphone. Microphone is a device that will convert sound energy into corresponding voltage energy. Here in this application, what we are going to do is, what they have done is, MEMS acoustic array will have an array of MEMS microphone. So this MEMS microphone will gather the sound from an amplifier or some loudspeaker, and they will be it will be detected by the MEMS microphone. This microphone data will be converted into voltage. This energy will be converted to voltage signal using microphone, and it will be processed. All the signal noise cancellation and everything, and will be done using this Vertex 4 FPGA and it will be stored in the computer for a future purpose. For example, if you're recording a song, this is the method. You can think of there someone is singing, and there's that sound will be collected using this MEMS microphone, and this processing of the signal will be done in the Vertex FPGA, and the processed signal will be stored in a system. So the one this is the my image of a single microphone which is used, and its number is S1689769. It's a microphone, and this microphone has a simple signal conditioning circuit. As I said, the signal from the sensors are very few milliwatts or very few microamps. Such type of we can expect signals in that range only. So these cannot be even transmitted for a 1 meter. It cannot be transmitted in 1 meter or even less than 1 meter. So this has to be amplified, or it should be converted into a form where it can be transmitted to the FPGA, or it can be any other signal conditioning circuit. In our case, it's an FPGA. So we have a first stage amplifier and a second stage amplifier, and this will be connected to an ADC signal. So the architecture working mechanism is this. So we will have a signal from the loudspeaker. The sound from the loudspeaker will be converted into electrical signal. Electrical signal using the array of microphones. So this array of microphones will determine the accuracy of the further signal, accuracy of the noise cancellation. Depending on how much number of microphone used, the accuracy, the acoustical accuracy will increase. So these data will be transferred to the FPGA IC, and there it will be processed further, and it will be stored in the system for further usage. So this in this way, so they have done is, instead of having a dedicated signal conditioning circuit for each and every sensor, they have utilized an FPGA. So what we can do is, what is the advantage of using the FPGA here is, if I want one noise cancellation is one thing, but this sensor, microphone sensor, can be data can be processed in any way. Any type of processing can be done. If you are using a dedicated ASIC system, then it will be confined for only noise cancellation. So, and efficiency. For example, if the microphone's ability is deteriorating during the overall course of time, you can change the program in the FPGA such that the final efficiency doesn't deteriorate. So this is the advantage of using the FPGA in such kind of places. The next case is the Spartan FPGA based NEMS accelerometer processing electronics for navigation. So navigation generally based on two systems. One is the gyroscope and another one is the accelerometer. The gyroscope will help us to detect the position of the instrument, and accelerometer will help to observe the movement of the object. So these two sensors play major role in navigation. So what they have done is, they have used an NEMS accelerometer. So they have designed, and they're processing the data from NEMS accelerometer and in the Spartan 6 FPGA system, and they are using that along with the some other gyroscope and control, and they have built a navigation system for it. And so they have this particular MEMS sensor comes with the temperature control. There's a MEMS sensor, and the MEMS sensor's temperature is controlled by some other sensor. So both data will be manipulated using Spartan 6. So here, instead of having a separate signal conditioning for MEMS system, they're having a single FPGA for monitoring the MEMS accelerometer as well as the temperature of the accelerometer in a single FPGA signal conditioning circuit. So in that way, it's the whole system, the MEMS accelerometer, temperature sensor, and the spot on 6 FPGA forms an ASIC system. So we were able to integrate two different sensors in a single FPGA system, and we are processing it for navigation application. So these are the building blocks of the system. MEMS, they're having a MEMS-based IMU, that is gyroscope, inbuilt temperature, gyroscope and accelerometer with inbuilt temperature sensor, and it will be fed to the navigation processing electronics. Again, it's a simple signal conditioning circuit which is required to convert the data of accelerometer's data and the and the temperature data, and it will be fed to the ADC. From ADC, it will be converted to the FPGA. According to so FPGA will have the program for the navigation system. So the input data from these two sensors will be calculated, manipulated in this FPGA, and it will be re-instructed to the system. For example, if need to change the position of the gyroscope, it will be read as a we can send it back to the navigation processor to change the position of the gyroscope. So in this whole system, all the sensors was data are manipulated using the FPGA, and we don't need a separate signal conditioning circuit, as well as we are doing, and we are also reducing the power requirement by using the FPGA in such type of applications. The last one is the control of MEMS disk resonance gyroscope using FPGA platform. Here, what they have, so here we have a disk resonance. The optical method of gyroscopes are very big and very power consuming. So we are having a disk resonance gyroscope. So this disk resonance gyroscope will deflect according to the according to the motion, due to the motion of an object. So what happens is, to calculate the amount of displacement, we will apply a counter voltage to bring back to its original position. You can see in this one. So let us assume only the moment of this center one. So it is rotating in a particular axis. So this rotation will be caused by any angular motion or any revolutionary motion. So to calculate the amount of revolution or angular movement, what we are doing, instead of measuring the deflection, we will be trying to bring back, they have tried to bring back the disk to its original position. This original, by doing that, the amount of voltage required to bring back to its original position will be proportional to the amount of deflection cost. If the deflection is more, we need more voltage to bring it to the original position. If the deflection is less, we need less voltage to bring it to the original position. So so that is mechanism. This is the mechanism of MEMS micro gyroscope. So we'll have a digital control. We have a separate digital controller for controlling, for measuring this deflection. So that is the purpose. That is why they have used this digital control of MEMS gyroscope. So this will first give an angular. This will measure first. This will measure the deflection. Change in this position to this position will be measured first, and according to the deflection, a signal will be the deflection will be detected. If the deflection is detected, a signal will be sent by this to move it back to its original position. The amount of voltage required to bring back to original position will be fed to the will give the amount of gyroscopic displacement. So this digital control is to calculate the deflection. And what is the use of FPGA here? Here we are using the FPGA for different things. So it is used as a testing platform. So these gyroscopes, over the period of time, will deteriorate the capability. We need to calibrate those gyroscope then and there. So what happens is, the disk is a mechanical structure. So it will be moving, it will have its own friction, and it will have some offsets over the period of time. So in order to correct this, we have a digital testing platform using an FPGA. We have a FPGA. So instead of changing it completely, changing the whole gyroscope completely, using this FPGA kit, what we can do is we can integrate this gyroscope to the FPGA kit, and the FPGA kit will act as will be loaded with the testing platform. So what will it will do is, it will the FPGA will generate a signal to cause the deflection, and it will measure the deflection voltage, the current voltage that is that corresponds to the amount of deflection. So comparing these two, so FPGA programmed in such a way that it will have the data. So it has sent an voltage to cause this much deflection. It will check whether the voltage acquired from the digital control of MEMS gyro is how much closely it matches with the with the given data. According to that, it will change the gain of the signal conditioning circuit. So in this way, we can we can calibrate an MEMS sensor using it. They have shown that we will be able to calibrate the performance of a gyroscope using a FPGA platform. So in all three cases, we have reduced is the amount of electronic circuit, and this will definitely lead to the amount of reduction in the power. So in this way, we can replace or wherever possible, we can replace the signal conditioning circuit with FPGA platform. So these as I did the literature, I could say that see that most of the works are not carried out in this area. So how we can proceed? So how we can proceed is, I'm saying this in the perspective of a research work. So instead of doing a research of designing a MEMS sensor or doing anything else, what we can do is take a data from take an application, and take an application, choose a sensors, and we can design a signal conditioning circuit for the sensor, for the application, and we can emulate it on the FPGA. So in this way, we don't need any real-time sensors, or we don't need any real-time sensors. What we can do is, there are n number of papers that has given the performance of a MEMS sensor. So take those results and try to put it in an application. For example, I have a pressure sensor, and there is an application called tire pressure monitoring system, where I will be measuring the pressure of a tire. So I have in the literature, I have an application that needs a pressure sensor for for monitoring the tire pressure. And in the literature, I will also have a sensor that will match the application. So what we can do is take these two data, take the application and data, and try to so this application need some performance. So try to design a signal conditioning circuit. For the signal conditioning circuit, based on the output, so the pressure sensor paper will have the performance output of the pressure sensor. Take it as an input to your signal conditioning circuit, and create a signal conditioning circuit for the tire pressure monitoring application, and check whether this performance of the MEMS sensor is applicable for a tire pressure monitoring system. And you can the tire pressure monitoring application will have a spec. Try to fit the spec with your FPGA implementation, the FPGA program, and try to emulate it. That is, download it on FPGA and check whether whether this input signal will satisfy the this for this input signal will the program developed using FPGA is used to control the tire pressure monitoring system. So it will give a good paper. So and ultimately, when we do a research, it's towards paper. So after going through these type of literature, I could see that this type of applications will give good papers. Here, this doesn't need any big investments, which we won't be able to get most of the time. So, but everybody will have access to an FPGA system, and we have n number of literature which have sensors for a particular application, and this particular application. So, what we are trying to show in such type of research is, instead of having a expected signal conditioning circuit, you can implement the same in FPGA with less power consumption and less investment. So this is the thing. So these type of approaches we have, but better reachability in papers rather than having a simple FPGA programming. We can try to combine all the three and give it as a paper. It will be a good research work. So this is the with this I'm concluding my talk. And if anybody is having any doubts, you can clarify now.
Thank you, ma'am. Dear participants, the session is open for your questions. Or if you have any queries, you can even post it in chat box. Patak ma'am has asked to share the PPT. At the end of the program, the PPTs will be shared to all the participants. Okay, ma'am. Sivasundari ma'am.
Thank you, sir. Thank you for giving
Thank
me.
you. It's a nice session, ma'am.
Thank you, sir. Thank you.
Okay, ma'am.
Okay. Thank you, sir.
No
Thank you so
question,
much.
we shall wind up. Okay, participants, the afternoon session will start by 1:45 p.m. So you can join the meet by 1:45.